Hello, everyone, and welcome back to our sessions of probability. Last time we learned how to find the confidence interval at any confidence level, like 90%, 95%, 99%, you name it, as long as it's less than 100%. But I told you last time that we make a huge leap of faith when we say, we know the standard deviation of the population, which is it's ridiculous, right? How can how can we know the standard deviation and don't know the mean? Which basically the standard deviation relies on the mean. So anyway, so we'll keep that for now. Okay. Notice that this is theoretic. I don't like to use the Z statistic at all for that reason. However, the theory of probability tells you that what if the distribution you are getting the sample from is normal and the sample size is large? And when we say large, we mean for all practical purposes 30 or more. In that case, we can use S in lieu of sigma. So we can say the confidence interval would be mu is greater than x bar minus z alpha over 2 times s over the square root of n um, less than x bar plus z alpha over 2 s over the square root of n. Okay, so that's what we do in case we have a large sample size, or everybody does that. I don't like it. I don't like it, and I will tell you why. Now, okay, so here we said, if I know the standard deviation, oh yeah, of course you know it, use the Z. If you don't know the sample standard deviation, I'm sorry, you don't know sigma, but the sample size is large, so you can take a sample, of course you know S, right? You can calculate S very easily. In that case, they tell you still use the Z statistic. So what do we do if the sample size is not large? So you know it's coming from a normal distribution. So your distribution is normal. That's fine. But you took a sample and the sample is small. You wanted to calculate S to use it instead of sigma. But because you did that, because the sample size is small, we say that S is a biased estimator of sigma. You learn maybe, I don't know, maybe I'll go over bias later, but bias meaning there is a consistent, like either overestimates or underestimates. We'll learn again about that. It's usually underestimate the standard deviation sigma. So instead of using the Z, we can use another distribution called the T. So you will be using a T statistic instead of a Z statistic. The T statistic, so if I have, let's assume this is my Z statistic. This is the Z distribution. The T distribution, you cannot draw it unless you know the sample size because it relies on a parameter. So the parameter for the T distribution, it has a parameter called nu, which equals one less than the sample size, and we call that the degrees of freedom. While the Z has a mean of 0 and a standard deviation of 1, the T statistic also has a mean of 0, but the variance, or the standard deviation would be the square root of that, is nu over nu minus 2. So let's say common sample size would be 5. 5 over 3 is 1.66. So the square root of that, which is roughly 1.25 or 1.3, would be the standard deviation, meaning the distribution is wider. The standard deviation, instead of being 1, depends on the sample size. As the sample size goes large and large, the standard deviation get closer and closer to 1 until we say in the limit as n approaches infinity, the t becomes a z. But the t would be more accurate if you are using the sample standard deviation. So in that case, we would say mu is greater than x bar minus t alpha over 2 and degrees of freedom. It's not enough to tell me t alpha over 2 because I don't know your sample size. Times s over square root of n, excuse me, less than x bar plus t alpha over 2. And sometimes we write n minus 1 because nu equals n minus 1 anyway, times s over the square root of n would give me 1 minus 100 times 1 minus alpha percent confidence interval on mu. The sample size is large and the distribution is normal. So both the t and the z work on the normal distribution. Okay. Now, so how do we calculate the t? Of course, there are tables that the problem with the t is that it's not like the z. Why? Because there is a degrees of freedom. So we cannot develop like a lot of tables, right? The problem is the table for the t will give you for say 2 degrees of freedom, 3, 4, 5, 6, 10, and then jumps to 20, then to 30, and then you see that practically it's a z. Also, alpha over 2, it gives you alpha over 2 if it's like 0.05, 0.005 or zero point zero 0.01 or but what if it's something in the middle? You cannot find it. While you can use the inverse for the z, you cannot use it for the t within the table. So the best you can say is that my value is between 5% and 10%, for example, but how much exactly you may not know. That's why we usually use calculators. So in the old days, that's what my understanding is that in the old days, we used to use the z if the sample size is large and we don't know the standard deviation. But now I say, since we have calculators and we have computers, why even use the z? There is no reason to do it because we know it's not correct. It's an approximation. And we say, oh, if the sample size is large, the approximation is small. But why do you actually approximate at all? I mean, it's not wrong, but since you have a better tool, use it. Suppose, let's take an example. This example says, um, let's say we have a sample of size, any number, let's make 60, whatever, any number. And let's assume mu equals 25.3, and we don't know sigma, we know S is 13.6, whatever. And I want to construct a confidence interval. I'm sorry, this is X bar of a sample. I'm sorry. And we want to construct, let's say, 90% confidence interval on mu. Notice, we say mu is greater than 25.3 minus t.05. If 90% confidence interval, it means 10% is out, 5 to the right, 5 to the left. Okay, the t distribution is like the z distribution is symmetric. So if I know t05, and this would be the negative t05, meaning with 15 degrees of freedom. So nu equals 15 and alpha equals 0.05. So we can use a calculator. Of course, we can we can find it right away if we have a computer, but I want to show you how to calculate the t from your TI-84. Okay, again, like we did last time, you go to distribution, go down to inverse t, because inverse of t will give you, it asks you enter alpha, which is 0.05, comma, and 15 degrees of freedom. Um, so This gives you negative, of course it's negative, but we don't write another negative, 1.753 times 13.6 over 4, which is the square root of 16. Notice, this is n minus 1, but you divide by root of n. So be careful. These are not the same. This is n minus 1, this is n under the radical. Less than 25.3 plus 1.753, 13.6 over 4. And of course, mu would be exactly in the middle of these. And of course, you can use the calculator, 25.3 plus, since this is negative, times 13.6 over 4, and you get 1934. Yeah, the World Cup in soccer was in Italy. Okay, crazy guy would love soccer, so. Okay, you delete the negative to make it positive, and you get 31.26. Notice that if I average these two guys, so if I say 31.26, of course, don't care about the and 1934 with the decimals, and then I divide by 2, I get 25.3, which is the mean. So that's your check that you didn't click a wrong button or something. So that in a nutshell, what I wanted to do here is to show you that statisticians say when the sample size is large and you don't know sigma, you can use S to estimate sigma, even though it's a biased estimator. But if we say the sample size is large, this bias is small, so we can use the Z. However, if the sample size is not large, meaning it's less than, here we said 16, okay? Usually it has to be 30 to apply this. So if it's small, you use the T because the T is wider. It's, inflates a little bit the standard deviation. So it is a pretty much unbiased estimator of sigma. The question that I want to answer now is, what if the sample size is large, but you don't know that the distribution is normal? Can you do anything? And here comes one of the most powerful theorems of probability, the central limit theorem, the CLT. L and T don't stand for lettuce and tomatoes. I know you're hungry, but no, it's central limit theorem. What is the central limit theorem? What does it mean? It turns out that we found through experimentation that if you get a sample from any distribution in the world, let's say the exponential, since you learned, and you calculate X bar. If you keep doing that day in and day out, calculate X bar, X bar, X bar for, a large sample. Let's say a sample of size 30 or 40, pretty much 40. I will tell you why we need larger for the exponential. If the distribution that we deal with is pretty much symmetric, like the uniform distribution, for example, or a triangular distribution, then n equals 30 would be good enough to approximate it, the central limit theorem to approximate. But the exponential is just one tail. It's very skewed. So you need a larger sample size, like 40. Okay, if it's something like the Weibull or the log normal or some other of these distributions that are pretty much symmetric, they are not symmetric, but they look like symmetric, 30 would be enough. But what does the central limit theorem say? It says that if you take a large sample from a given distribution, you don't even know what distribution it is. All what you know is that it's not normal. Okay, it's not normal. And you take a sample size, you calculate X bar, you calculate X bar tomorrow, you calculate X bar the following day. You keep doing that, and then you draw a histogram. Yes, you got it. The histogram would look normal. You say, what? So my individual values were exponential. But when I calculated the mean of that exponential, and then the central limit theorems, they say the mean or the total. You say, okay, the total, it's like I'm multiplying by n, so it's a constant. Yeah, so it's like I'm enlarging the distribution. It's not a big deal. If the total is normally distributed, then the mean would be totally distributed, right? But not only that, the mean of the means, notice I'm drawing here X bar from E. So I took a sample of size 40. I calculated X bar. I call it X1 bar. And then an hour later, I took another 40, calculated X bar, and then calculated X bar. And I keep doing that and plot the values of X bars as a histogram. My histogram would look something like that. It would look like a normal distribution. Wow. Not only that, the mean of these means, we can call it X double bar because it's the mean of the X bars, would be mu, or the expected value of it is mu. Wow. So you are telling me I can find the mean of the exponential from which I took a samples every day? Yeah, because the mean of the means is the mean of the exponential. Not only that, the standard deviation of those means would be sigma, which you don't know, over the square root of n. It's an estimate. So if they give you the standard deviation, I'm sorry, if you calculate the standard deviation of these x bars and you multiply it by root n, you get the standard deviation of the original distribution. I know it's a little confusing, but that's very powerful. Meaning I'm getting samples from a distribution that I don't know anything about. I plot the histograms, or I approximate it by a nice curve. It turns out to be a normal curve. The mean of it is the mean of the original distribution that I don't know even its name. I have no clue what it is. And the standard deviation of the means is the standard deviation of the distribution divided by root n. So I don't know the distribution, but I know its mean and its standard, or I can estimate its mean and I can estimate its standard deviation. That's how powerful the central limit theorem is. In fact, if that is coming from an exponential distribution, I know for the exponential distribution, the mean equals the standard deviation. So if that mean is 10, and I'm taking a sample of size 40, that would be 10 divided by the square root of 40. So when I get this number, I multiply it by the square root of 40, and I will get roughly 10. And I say, oh, the mean equals the standard deviation. It might be exponential. I know that for that distribution, the mean equals the standard deviation. It's very powerful. So why are we saying that? Because statisticians say, oh, so now if I'm taking the samples of a distribution that is not normal, all what I have to do is to make sure that the distribution, that the size is large, and I can construct a confidence interval for them using this equation. Because now I can use the z. Why? Because the means are normally distributed. So now, if I know the standard deviation, which is impossible, but we say if we know it, we use the z. If we don't know it, but we have large sample size, we use the z. If we don't know it and we cannot use large sample sizes, so we use small sample size, we use the t. If it's a non-normal, but we take a large sample size, we still can use the z. I prefer to use the t, but you still can use the z. Finally, the $64,000 question. What if the distribution is not normal and I cannot take a large sample size? What can I do? Unfortunately, you cannot use the central limit theorem because it works when the sample size is large. In that case, you use other stuff that is are beyond the scope of this course, you can use something like bootstrap simulation, and that will give you you can use that, for example, to find a confidence interval, but we are not going to cover that here. We need to see to show a lot of simulation. Unfortunately, um, I don't have a software. I used to use a statistical language called R. I have R in R Studio here. Maybe I can make some series on the use of the language, or you can use Python. Um, R is a computer language that was developed specifically for statistics, so it's very powerful. Of course, the Python can do the same thing, but I'm saying you can use, if you know this, we can do a lot of simulation to show you that really we are going to generate random samples from an exponential distribution and plot the means, and you will see that the means will be normally distributed. I can show you how to do the bootstrap confidence interval. So maybe I'll think about that. Or if you want me to do that, maybe you can drop me some comments and I will think about teaching you quickly how to use R or R Studio if you don't know how. And we can do some simulation, some nice work there. Anyway, I will stop here and probably in the next session we'll say, okay, what if I have two distributions and I want to find the confidence interval of the difference between them? Because I need to know, is really one is higher than the other, or I can consider them to be equal. And maybe also to look at the confidence interval on standard deviation, not the mean. Notice we did a confidence interval on mu, but what if I want to do a confidence interval on sigma, which I don't know, but I want to have, say, a 90 or 95 or 99% confidence interval on sigma. We'll learn about these in the next following sessions. Thanks for your time. Sorry if it was a little, we didn't have more than one example here, but again, if I give you the numbers, all what you have to do, you can plug them. You know how to find the z, you know how to find the t values, and the rest is history. Thanks for your time and hope to see you soon. Goodbye.